Okay. Okay, so today we continue lecture 4. So I think I'm going to start the topic. Okay, so we look at the non-degenerate. So I'm not sure that you know these words. What is the perturbation? Do you know this? Okay. So it's like you have something that actually you know exact, and you touch something with little small, very small thing. And then what you need is to solve for this problem. And this small thing come with like a parameter, suppose lambda. Okay, right, something like that. Okay, that is the thing. So as I mentioned earlier, actually, well, very few examples in quantum mechanics that you can solve exactly, right? Like particle in the box, harmonic oscillator, hydrogen atom, a part of that, and no. Then that is a problem. Then we need a technique to extend mathematical tool to study further complicated problem, right? Right, that is a thing. Okay. So we okay, so we start with some independent showing equation. I mean, so it means that actually you could get the solution in the exact form. So let's say that. So this is labeled by naught here. One, where the wave function must satisfy this autonomous here. It's not right. It's very standard. And define as an exact eigenvalues or unperturbed. Eigenvalue, okay, unperturbed. It's the same word. Okay, so suppose Now the system is slightly perturbed in potential energy. Okay, like I put the picture here. So, but we're going to look at much more in terms of math now. The question, what would happen to the eigenvalue? And of course, eigenstate of the system. Okay, so now we have a new, sorry, I should put have to be here, the operator. So here, so this is perturbed Hamiltonian. Okay, very simple. So as I mentioned that, so this perturbed Hamiltonian can be split right into two terms. Okay, so you can split this Hamiltonian into the one that actually know how to solve it exactly, and another one that coming in with the parameter lambda here, like that one. This called perturbation term. So where is small, okay, parameter and will be taken to will be we'll take it to be 1 at the end. Okay, so in principle it means that you put this parameter at the beginning and you take the limit when you finish your computation, and then take the limit to be 1, and then that's it. So now what we are going to do, what we write in terms of expansion, yeah, and of course that your energy can be so, well, this is going to say that this is the first order, right? Well, there's some word actually collection or contribution or perturbation. Okay? And of course, then the higher term, you get second order and third order, right? So it depends on how accurate that you need to consider your system. Sometimes we need only for only the first order. All right, so now if we put the eigenstate and eigenvalue of your system in this way, so let's see the equation that you could have. So then this equation can be put okay, in this way. Very simple. What you need is to expand the bracket two sides, and then you will get okay. So you're going to have this. If you're expanding carefully. So now you can easily see that so if you look at order 0, you will get this standard equation. Yeah. And so you knew this, right, what it look like. So next to move to the first order of the expansion. Okay. So if you want to solve for this, we're going to solve for this one. So it means that you can you can spot from this equation that if you want to solve for this eigenstate, you need to multiply the complex conjugate, right, of this bit throughout the equation and do the integration, right? Okay, so what you're going to get is that. So you're going to have this one. Mm-hmm. So basically, that just since this is constant right here, you can pull out of the integration. This is the same, and if you look at this term and you look at this term, actually they are the same because one you add this operator on this, right? You pull out E0 in, and then it's going to kill that term. So at the end, so you will get that the first correction of state or eigenvalue is this one. All right. Now you get the first correction of eigenenergy. Right. So next, we get the first this one, then we need to solve for this one next, right? Then we need to solve. So for this one, what we're going to do is that from this, you can write thing in this way. It's very trivial. Oh no, this one. Right. Yeah. And also put this, okay. You expand the first, correction of the eigenstate in terms of the well-known one in the some linear combination to be determined. Okay. So now what you're going to do is that, so from this, you're going to do this. You apply this compact conjugate. Okay, to the left-hand side of above equation. Okay, yeah. And so you act this, right, you will get E0M. So what you have is E0M, 0M, M, N, okay? From the left hand side. On the right hand, so what you're going to get is that since this is constant, then we check out, and then okay, and then here, okay, so this give you the delta function, right? Then it's going to select the term that, well, normally, yeah, it cannot, n cannot be equal to m, right? This, then, I mean, this 0, right? Because we put this condition on the way that we expand. So now you're left with this term, right here. Oh, this should be 1, right? Sorry. Should be 1 here. And yeah, I think it's correct now. Should be 1. So what you need is that you need to consider this integration. So you need to put this equation. So okay, so you put this, and then what you get is you pull out the summation, and you will have M. Oh, you get CL here, right? And then this gives you ML, right? And if when M equal to L, then this is going to give you summation of this C ABM, right? Yeah, you just change L to BM. Okay, so now what you have is okay. So actually, there is a summation here, but I already exclude in the case of n equal to m because it's not allowed, and then we're going to get right here. So finally, we could get the coefficients in this way. Then your first collection of the eigenstate going to be this one. Okay. Then in the first order, we know how to solve for the first correction, right? Both of the eigenstate and the eigenvalue of the system. This is M. Okay, because you have a minus sign here. So next, let's have a look at the example, which is I took it from Griffith. If you look at the textbook of Griffith, so you're going to have this system, and then it has been shifted up by, the potential have been shifted up in this way. So this means that, so at the beginning, your Hamiltonian is very simple, right, in this region, and then you know what is the solution look like. Here is a solution, right? So now once you have this kind of shift of the potential, you get which is, you can think that actually you have to add the constant value of the potential value here into the system. And then you can consider this V0 as a perturbation term. And so if you want to compute this, the first correction of the eigenstate, you can do directly. Okay, so you put that and then you get this very simple. And it turns out that you get V0. I don't need, I don't want to do the integration for you, but you can do it yourself because it's not difficult. So then it means that your energy level is going to be this one up to third order of expansion. Okay, roughly speaking, but this is kind of really exact that you can do. And then of course, then you can solve for, this function as well. But I'm going to leave you to do it yourself. I don't that it's going to be difficult. So it means that your new wave function here is going to be an eigenstate of your new Hamiltonian, right? Once you combine that one and that one in terms of the linear combination, right? Yeah. Then you need to check that as well. So from this example, very simple. Then we're going to the second contribution, all right, in the expansion. So if you look at the equation that expand in that bracket, you will have equation something like this. Okay, if I recall things correctly. Right, so now we want to solve for this eigenstate, the second correction term. So, well, we're going to do more or less the same. You apply the compact conjugate of this thing. All right, and then, okay, let's do it. Oh, sorry, this is 2. This is 2. Okay. Okay. And so you add this, right? And then you get E0 out, right? And then you will get this thing. And then you see that which is actually the same thing with this one. So it's going to cancel each other. Right. Then what you have in this situation, so you're going to left with this term, right? So you're going to have this. And this one, you move this to this, going to get 1 because normalization condition, right? Then you get only this. And this as well, you move out of the integration, right? And you get this, okay? Now you can see that actually you can move this term to this side and you can write down what is the E2. But you know that actually you can expand this psi 1 right here. In this way, in terms of the exact state. So it means that here all the thing here, so you will get what? You will get delta function. So you get E1 m not equal to n of C1 delta function mn. Am I correct here? I think so. Let me have a look. Yes, I think I'm. Oh, this should be 1, right? Yeah. And so, well, since m cannot be equal to n, then whole bunch of this going to be 0. So then your second contribution or second correction term from this, I mean, is this one. But again, so you need to put expansion into this. So you're going to okay. So you're going to have this. And so you know what is the C1M, right? We did solve already what is the C1M. This here, big huge term here. You put C1 into that equation. You will get, so, oops, sorry. This is your C1. Then your E2 is here, this term. And so it's going to be huge. Okay, this one. So I use different in integration variable. The first, well, it look like you have to do the square of this integration, but you need to be careful because it comes from different, here you do integrating with respect to the x, right? And then once you put that, you have to do different variable as x and y to make sure that you don't get things mixed up. All right. Okay, very good. It's going to be, okay, next. So now I'm going to put this as a Dirac notation. So it means that your E is going to transform into this. The first one is M, X here, X, N, and this Y, Y, yeah, and this whole thing divided by this. So next I'm going to shuffle things around because this is going to be the energy eigenstate, right? For this Hamiltonian, then it means that, so what I'm using this completeness, right? Okay, so then this equation can be rewritten okay in this way. Okay. I mean, you take out this completeness relation, take out this completeness relation, and then you sandwich these two things together. So now you get your E2 in this way. And of course, then you can write your E1 in your Dirac notation as well, right? It's not difficult. You can try yourself. So in the E1, you're going to have only this one term, right? Because you put so next. So for this function, so we're going to recall this. Okay, so again, recalling this equation. So what I'm going to do is that I'm going to multiply this bit, this function from the left-hand side. So I'm going to have this, okay, and so here I'm going to have this, okay, in this way. it should be M. Sorry, M. So this orthogonality, this go away. And of course that, actually what you need to do, you put the integration, you can do it anyway. So, so again, this one act on this, right? This one act on this state, you get E0 n, right? And then we get here. And on this side, you have this equation left. And this one. Okay. What we are going to do is that we're going to do the same trick that we did for the style one. Now we're right, okay. Right, you put but different constant here. So once you do this, so you can. So what you have is that oops, sorry. This. Okay. It's a bit long, but it's not difficult to follow. It's very straightforward, right? So this whole thing going to give you a summation of this CL to delta function. This side, right here. And this whole thing, again, going to give you summation C1 L ML, okay? Okay, and then this you cannot do anything because you can just pull this constant out, right? So basically, So you got at the end is that yeah. So now you can solve for C2M, right? By moving this whole thing into this side. So then what you have is C2M. Then should be M. Maybe it should be N. Let's check. And then this go. Oh.ฮัลโหลครับอ๋อฝากกับรปภไว้เลยได้ไหมครับพี่เก็บตังค์ไหมครับโอเคครับ if so the first term coming from here and the second term from this one if I think I going to yeah I think it's should be correct right you might need to check a little bit it's very huge oh not actually I forget to divide by so you need so I forget to divide by this whole thing so you need is I think it's going to be square and this going to be mn, right? Okay, I think this kind of correct. If not, then it did not. Okay, so it means that if you know how, if you can solve for this C2M, you know how to get this this second order. Just put in there, right? Multiply with you know exactly. Okay, that's it. Okay, let's have a look at example. So you're going to look at the anharmonic oscillator. So your Hamiltonian is given into this form. Okay, so this is going to be your exact Hamiltonian, and then this is, of course, is the perturbation term. Okay, you know that from this, the eigenstate for this, and of course, okay, these are the well-known solutions for the harmonic oscillator. It's a polynomial, right? Okay. Okay, and so, well, so suppose that we are interested in the Gauss, okay, energy, which is actually this one, and you know that the Gauss state wave function going to be okay as well. Well, you know how, well, I hope that you get the point that why in quantum system Gauss state energy cannot be zero. All right, how you get that physical idea behind this thing? It's just not mathematics. There is something that actually constrain that telling you that, oh, this cannot be zero. Otherwise, it's going to violate something, right? Okay, so what we are going to do is that we're going to compute the correction of the Gauss state from this term. Actually, you can do the correlation of the higher term, but it's going to be very difficult. Then we are not going to do that in the class. Then you can try it yourself at home. But we can do simple thing, of course. So what we're going to do is that, yeah, so for this. So what here. Okay, we're going to compute. Then, you know, okay, this is the perturbative term right here. So after you plug this whole thing and then do the integration, you find out that actually it's going to give you 0. Interesting. You need to check by yourself that actually this is true. Okay? What does it mean that no contribution? Right, to the cloud state for this cubic term in the Hamiltonian. So your cloud state is going to be exactly the same for the first, perturbation. But the question is that, what about the second order? I don't know, you need to compute yourself, okay? So, no contribution from the cubic term to the cloud state, okay? Next example, which is very simple. So you have particle in the box. Here. Then later, you apply electric field. In this direction. So now your Hamiltonian can be put in this way. So this is going to be your perturbation term. And then you can compute the Gauss state, the collection, the first collection. Energy. So your EM and then so you know what is the wave function for this infinite bell, right? Once you put this whole thing, then you get, what is it? A, what 2? So this is the contribution term to the energy level. Is going to be shift, right, by this thing. So shift term. So it means that, so normally you might, so your Gauss state is going to be like the energy state is something like this, right? Once you apply the electric field, it's going to shift your Gauss state up, and here as well. Right, the first excited state up. How much is depend on the strength of the electric field and the width of the well. Right, that thing. Okay, so I think we kind of have enough for a case of non-degenerate. Next, we're going to the case to consider the case of degenerate one, which is a bit tricky, a bit not too difficult. You know that the difference of between degenerate and non-degenerate, right? Tim, can you tell me the definition of the degenerate and non-degenerate thing? Can you? What is the difference? Again, please. There are more than one state actually sharing the same again state, right? Okay. Okay, good. Okay. So we consider in the case that if the unperturbed state are degenerate, like you have the same eigenvalue so this is going to cause a problem in the period technique if you this this kind of thing. So we need to take care of this thing. Can you see what is a problem if we still using this kind of technique with this? Oh yeah, of course. Then that thing going to blow up, right? It's going to cause you a problem. So first, let okay, so now we consider two-flow degeneracy. I mean this two-flow degeneracy here. So it means that you can have more than two, right? Actually, you can have more than two, right? But in a simple situation, you have this. Okay, these two different states are orthogonal to each other. And I mean, so is still a solution. All right, because this is solution, the linear combination of this is going to be still the solution, right? So this means that you're going to have this right here. Okay, this is all we have for unperturbed. Right, this is unperturbed system. So next we're going to look at the perturbed one. Okay, so your Hamiltonian. This is the perturbed one. Right. And then what we are going to do is going to solve this again. This can be split again in these two parts. The first is the exact part and the perturbed terms. And so your E going to be E0, E1, E2, and this, the same can be putting into this. Okay. Again, we put all this equation back into that one, and then what you have is more or less the same with we do have in the previous case. But yeah, you need to be a bit careful of the degenerate behavior of the eigentrace or the eigenstate. Okay. So after you expand all the brackets, so you look at the first, the zero order, you will get this unperturbed system, of course, right? And you look at the first order, you will get exactly the same that what we have in the previous case if you look carefully, right? What I'm going to do is that I'm going to apply this A, label A, right, from this side and this side and this side A, yeah. And it turned out that once you add this operator, you will get E0, right? And then this going to kill with this term again. So it means that what you have is you have this. Okay. And so, but you know that actually this this unperturbed state here can be put in the linear combination of A and B in this way. So you put that back here. So we have alpha, A, beta. Oh no, not star here. Sorry. B. All right. Alpha, beta. Okay. And once you move this whole thing into inside the bracket, you will see that the second term will go away because the orthogonality condition, right? When you move this to this, it is going to go away. Then on the left hand side, you will have only the alpha term, left, right. You have only alpha. You have alpha E1. And on the right hand side, you're going to have a huge term left, something like this, alpha beta okay, yeah. So similarly, so you may wonder, actually, you may have the question, why I have to multiply this phi A? Can I do with the phi B? Of course we can do with the phi B. If we do with the phi B, so what we're going to get is this equation. I'm going to skip it because it's going to proceed the same step. Okay, so you will get this equation. Now it seems that you can more or less put this couple equation in a metric form now. So we introduce okay, I introduce this kind of element matrix, Wij. Okay, so it means that once I introduce the, whoa, shit, sorry. What time is it now? Okay. If I introduce this object, so I can rewrite things in this way. AB. Okay, so now what we have is this very short equation. Okay. And so, of course, that you can solve for this. Right, you know how to solve this, right? Can you tell me how to solve this? If you want to get this thing, this is no, actually, what you need to compute is this whole bit here. I mean, you need to solve actually for this E1 here in terms of this thing. If you look at this, so you can say that, oh, this is the operator that act on this state, give you this constant, right? Which should give you, this is the eigenstate for this operator. Look, how to solve this? Well, it's not difficult. Actually, if you don't know how to solve from the method, you can start from these two equations. You can multiply this thing, and then, but I left you to think yourself what kind of condition that you could get E1 in this way. Okay, so you have this out. So now you look at your Hamiltonian, which is actually, and you say that your lambda is ranging from 0 and 1. Suppose, right? It means that now your energy going to, suppose this is the energy of your system. And this is going to be lambda 0. Yeah, and then this is lambda 1. So your energy will be split in this way. Okay? This is lambda splitting. Energy splitting. So the question is that what happened? So the question here, what does happen if you set alpha to be 0? It means that now there is no degenerate anymore. You should get everything back to the previous case. Then I'm going to leave this as a homework for you to prove yourself that actually once you put alpha to be 0 or beta to be 0, you will get the non-degenerate case. It's not difficult, but just a few steps of maths, then could be fine. So what time is it? Let me, oh, it's going to take quite a while. Okay, so let me give you example, and then we stop for today. But I'm not going through all the detail of calculation because it's not difficult, but I'm going to point the core idea, what really happened. So again, I took this from Griffith textbook. So you start from a box, 3D box right here with A, and A, right? And then what, of course, that this is potential. Okay, this is standard potential. So what happened is that, so if we shrink if you shrink the potential to just to this half, okay, on this side x and y, so what, yeah, you need to compute so from this, you know what is eigenstate, right? And x and y. Okay, this is your eigenstate, which is very trivial, and your eigenvalue, which is okay. So you've you find that the cloud state which is actually this term, which is correspond to this one. This is your cloud state 1, 1, 1. And so if you look at the first excited state, you will get MA, which is coming from this one, 1, 1, 2, 1, 2, 1, 2, 1, 1. Okay, so I'm going to call this A, B, C. Okay, you see that in this case we have 3, 4. Okay, 3, 4 degenerate. Okay, so now this is the perturbation term. Okay, you shrink only in the x and y, but you keep that same. Okay, so what we're going to compute is the contribution to the Gauss to the first excited state. Okay, because the first excited state you have degeneracy, right? And then we need to see first order here. Be careful. This is unperturbed, but the first excited state. This is the first order of correction. Okay. So okay. So you need what you have this relation, and then you plug all the equation that we know here, which is very long, then I'm going to skip it. But once you finish the calculation, you're going to have this over 4. I think this is the okay. This is the first. Should be the first collection of the Gauss state, right? Okay. So it means that your Gauss state will be shift with this. Okay. And so next we're going to look at the first collection of the first excited state, which is I'm not going to compute, but I know that actually threefold. Then you get alpha, beta, gamma. Suppose that actually you write that actually the first Gauss state can be put in this linear combination of this alpha, beta, and gamma. So you have this matrix, right? Yeah, you. So alpha, beta, gamma. And so you're going to have the element. So what you need is to compute all the element in this. So you find that for the diagonal, I mean in the you will get this. Okay. And of diagonal will be 0. Yeah, and so I'm not going to do it. I just suppose that you can do it by yourself. I just put it and you can check it at home. So it means that finally, what you're going to have is that this is going to be your metric. Okay. So you need to solve for the eigenvalue. And then you find out actually the eigenvalue in this case is this one. So it means that your is plus lambda 0 and no lambda kappa minus kappa. Okay. Well, don't forget that once you compute the eigenvalue, that you need to multiply this whole factor back, right? Then you get this contribution to the first excited state, right? So let me draw so what we have is that, again, this is a lambda. Suppose that, so you have this to be E0, 1, and then so you get okay, you see that it's split again, right? Splitting. Okay. So later on we will see more. We're going to discuss more in terms of what kind of physics that we're going to have this, what kind of effect that we could observe in the experiment to see this kind of splitting of the energy spectrum, right? Okay. So I think that's it for today. And so of course, next time we're going to look at, yeah, as I mentioned, like a hyperfile structure, which is actually involve this kind of business when you, of the hydrogen atom, like when you add like a spin coupling into that Hamiltonian, then you treat that spin coupling to be like a perturbation term, you're going to have this high splitting of energy, and then it's actually can be observed in the experiment. Okay, thank you very much. Any questions?